So here we're going to talk a little bit about Gauss's law and working through the different examples of things that one might need to do on various types of homework problems. So in integral form, we have Gauss's law specifies that the flux of the electric field through some surface is equal to the charge enclosed divided by epsilon naught. And I'm going to choose to write that is the integral of rho d tau, where the integral of rho d tau is going to be the charge that's enclosed. And this integral is being done over some volume that's bounding this surface here, so that we can see that the flux through the surface of the electric field has been created by the charge that's been enclosed, which we're going to find by integrating rho d tau. Now, the key thing is that while this equation is always true, it is useful in finding the electric field in three symmetric cases. And so the purpose of these notes is to work through a couple of the examples of those cases, or to give you the basics for how you would continue working on these problems in those three cases. And so the first of these cases that's important is spherical symmetry. And in spherical symmetry, we have some sort of sphere that has charge, say, inside of it somehow. The sphere might be of some radius r. We might be interested in finding the electric field at some Gaussian surface G1, say here. And so the first thing I'm going to do is sort of talk through what happens on the left-hand side. So I'm going to think a little bit about what happens on this left-hand side in each of the cases. So in spherical symmetry, the integral of E dot dA is such that the electric field would always be perpendicular to the surface. And if I have spherically symmetric charge distribution, then the electric field would be constant and parallel to the surface, or parallel to the surface's perpendiculars. And so the electric field gets to be pulled out of the integral, and I'm just going to get E times the surface area, and so that surface area is 4 pi little r squared, where little r is the radius of this Gaussian surface that I'm interested in computing. And then on the other side of the equation, I would have to integrate rho d tau, and I'll talk about integrating rho d tau separately. In the case of cylindrical symmetry, now we have, in principle, some sort of cylinder, and it's important that, at least in principle, or for the application of Gauss's law, this cylinder has to have infinite length. Now, there's a little bit of trouble with having the charge proceed all the way out to infinity. It causes a few problems in how we think about the surface, but we can use this as a good model anytime we are close to the surface of the cylinder. So again, possibly my charge is inside of this tube here, and this tube might have some radius capital S, and I might be thinking about some Gaussian cylinder of radius, say, little s. Let me let the tube have a radius of, let's give it a different letter. Let's call the radius of the tube A. So if the A is now the radius of my tube where the cylinder is. And so again, the electric field is going to be, by symmetry, perpendicular to the surface of the cylinder. So when I go to compute the flux, I can again pull the electric field out, and I'm interested in the surface area of the cylinder. And so for a cylinder, the surface area would be 2 pi times s times some length, where L is some length here that I have. Now, in principle, because the cylinder has an infinite length, this L would technically be an infinity. So what I might be thinking about here is some limit where the L is going to go to infinity. Now on the other side, though, of this equation, I'm going to be setting this equal to the integral of 1 over epsilon naught rho d tau. And in the case that I have cylindrical symmetry, my integral that I need to do, whatever rho is, has to be a function of the S. So my E times my 2 pi SL, this rho here has to be a function of S only, because otherwise I don't have cylindrical symmetry in terms of my charge distribution. When I do this phi integral, that's not a problem. The phi integral is going to go from 0 to 2 pi. The z integral here is running down the length of the tube, right? So I'll make these a little bit bigger. I'd run out of space. dz, d phi. For the z integral, what I'm going to do is I'm going to think about running the z integral from 0 to L. And then the s integral is going to run from 0 to, say, s. The key point is that when I do this z integral, I can do the phi integral and the z integral at the same time. I'm going to have 1 over epsilon naught. I'm going to get a 2 pi when I do the phi integral. When I do the z integral, I'm going to pick up an L on this side, and then I'm still going to be integrating rho of s times s ds over here. But the key is that the L that you pick up over here in the length of the cylinder for the surface area, and this L that you pick up when you do this integral over the rho with the dz, those L's are going to cancel off. And so the key idea is that you will always be in cylindrical symmetry in a case that even though the cylinder is infinitely long, you can think about integrating some length of the cylinder and then taking a limit where that length goes to infinity, but that length is going to end up canceling off. If that length is not canceling off, then you don't have cylindrical symmetry and you can't actually use Gauss's law to solve for the electric field, even though Gauss's law might be true. So in the cylindrical case, even though the cylinder is infinitely long, we can integrate the cylinder from 0 to L on both sides for the dA and for the integrating rho d tau. And so when we integrate rho d tau, we're going to pick up a length, and then we'll be able to cancel that length off. And then the final case here that we want to do is planar symmetry. Planar symmetry is, in a sense, the easiest, but it's a little bit difficult to visualize sometimes. So what we have in mind here is that we have a surface on which there is charge somewhere on this surface. And this surface has to extend again to infinity in all directions. So this surface is going to extend to infinity in all directions. And it might have some charge density on the surface, but the key, if it has planar symmetry, is that it has to essentially have constant surface charge density on the entire surface. I'm going to assume this charge density here is sigma. Now, the tricky thing here is to understand how to employ the integral of E dot dA and the integral of rho d tau. So the tricky part of this one is to view the symmetry as or the Gaussian surface as a box that goes through the surface, right? And so because of the infinity in each direction, the electric field created by this charge is going to go out through the top of the box and out through the bottom of the box. So the key thing with planar symmetry is because the charge is there's always charges on the left and the right to cancel off any component that's not vertical. You get an electric field that's always vertical. Go back for a moment here as sort of an aside and think about a line that has positive charge on it. And let this line go to infinity in both directions. And think about the point up here. This point up here, I can always pick a little bit of charge over here that makes the electric field go this way, and I can always pick a little bit of charge over here that makes the electric field go that way. And so the net electric field is always going to be perpendicular to the line. The same thing's going to happen if you have a plane, right? You can do this in the x direction, do this in the y direction. And so everywhere at any position above the plane, the electric field is going off in either direction. And so now what happens is that the top of the box has some area A, and the bottom of the box has some area A, and the A vectors point perpendicular to the surface, and they point a line to the electric field. And so if we have planar symmetry for a non-conducting surface that has charge sigma on it, we would have electric field that comes out the top of the box, my Gaussian box, and I would have electric field that comes out the bottom of the Gaussian box. And in both cases, the electric field is aligned with the area. And so I'm going to have E times A at the top on this side, and I would have E times A at the bottom on this side. And so I would have twice the electric field times the area. And then on the other side here, probably the easiest way to think about this is that the integral of rho d tau is Q enclosed. And I could start at this point here. So if I stop at this point here, I've got problems on both sides, right? Because if the plane really goes to infinity, then this area is infinitely big, but so is this charge. This charge enclosed is also infinitely big, but I'm going to assume that those are infinities that I can make a ratio out of. And so if I solve this for the electric field, I would take the area and the Q and put them on top of each other and just say that that is equal to the surface density charge sigma. So the electric field formula would just be sigma over 2 epsilon naught in the case of a non-conducting plane with constant charge density sigma. And so the sigma is perfectly well defined. You can have a certain amount of charge per unit area. It's just the area is infinitely big, and so the total charge is infinitely big, but that ratio is going to stay the same. So this is really the only thing you can do for planar symmetry if the surface is non-conducting. I'll quickly point out what to do if the surface is conducting. If you do have a metal slab, then a couple properties of conductors which are important. One is that the electric field is equal to 0 in the metal. And the other is that the charge is on the surface. So let's suppose that I create a metal slab that's infinitely big, right? It's going to go to infinity in all directions again. But it's a real metal slab in the sense that it has some depth to it. So it's going to go to infinity in all these directions over here. But it's this real metal slab that has some depth to it. And so now if the metal slab has, say, positive charge on it, there's only two sides of the metal slab. There's only two sides because the left and right side goes to infinity, the front and back side goes to infinity. So this bottom also is going to have positive charge on it, right? So there's going to be positive charge on the top of the slab, and there's going to be positive charge on the bottom slab. And then what you do is you draw your Gaussian surface in the same way. You use a box again, but you use your Gaussian surface where the bottom here is inside the slab. And since the electric field is 0, then the electric field times the area at the bottom is equal to 0, because the electric field is equal to 0. And so now the only side that has any flux coming out is the top, and the integral of E dot dA for a conducting slab is just E times the area of the top side, and that's now equal to charge over epsilon naught. And so the electric field above a conducting slab is 1 over epsilon naught. Q over A is sigma over epsilon naught. This formula for the electric field, if you flip up in the notes a little bit, is twice as big as the formula for the electric field in the case where we have a non-conducting slab. Because in a non-conducting slab, the electric field can be going off the top and out the bottom, but here it's concentrated to where it has to go off the top. So the electric field created by a metal slab, this would be the electric field, say, above a metal slab, is going to point perpendicular to the slab and have a value of sigma over epsilon naught. So now these are the useful things to do with the basically the left-hand sides. All right, so what we started off by saying is, how do I compute these left-hand sides? Right, this integral of E dot dA in all these different cases. Now, for the right-hand sides, we're integrating rho d tau. We got to somehow find this charge, which is the integral of rho d tau. So now if we have spherical symmetry, then rho can only depend on r. And so when we integrate rho of r squared sine theta dr d theta d phi, the theta phi integrals are going to do their normal thing. The theta and phi integrals are going to do their normal thing and just spit out a 4 pi, and what we're going to be left with is an integral of rho of r squared dr. If we have cylindrical symmetry, then the density can, again, only depend on, say, the distance away from the central axis. And so the integral of rho d tau in cylindrical symmetry is, again, going to be a triple integral, but 2 of the integrals aren't going to matter, right? We're going to integrate rho of s ds d phi dz. The z integral is going to go from 0 to L, the phi integral is going to go from 0 to 2 pi, and the s integral is going to go out to whatever Gaussian surface we are integrating at. And when we do these phi d phi integrals, we're going to get a 2 pi off of the phi integral, we're going to get a length off of the z integral, and we already talked about how we'll use that length to cancel out things. And what we're left with integrating is just the density as a function of the radius. And so for both cylindrical and spherical symmetries, the integrals that you have to do, I lost an S here. The integrals that you have to do are just the integrals of a function of one variable, the radial variable, away from, say, the central point in a sphere or away from the central axis in the case of a cylinder. So I'm hoping that these ideas are going to help you if you review them in working on the Gauss's law homework problem.